Hi students, today we'll discuss a very interesting question from rolling. So let's jump directly into the question. The question says that this is a solid cylinder of mass m and radius r. It is standing at the very edge of the table. That means its center of mass and the edge of the table are on the same line. So if you see in the 2D, the figure looks like this. This is the center of mass and the edge of the table is like this. So this diagram that you are seeing is in 3D and this is in 2D. So center of mass is exactly at the edge. Okay, so 50% of the cylinder is outside the table. Now there is some wind, slight wind blow or something. For that, the cylinder rolls, and cylinder rolls with respect to the point A. So the question is asked that what is the angle by which the vertical line or the radial vector, this red line, will rotate with respect to the vertical. So by what line the cylinder will rotate with respect to the vertical at which the cylinder will be on the verge of losing contact. Now what is the concept of losing contact? Concept of losing contact is that normal reaction acting on a body must be equal to 0. So if we take the situation where the body, this cylinder, is on the verge of losing contact, it will look something like this. So this is a 3D diagram. I minimized the diagram, and this was the initial situation. Now when this cylinder will be on the verge of losing contact, the cylinder would have rotated by certain angle theta with respect to vertical. So this white line is the vertical, and now this is the center of mass line, the radial vector that passes to the center of mass. So you can easily understand this is the angle of rotation. This is the angle of rotation, and we need to find out this theta. So as the cylinder is rolling at this time, there is omega, right? And also center of mass will have some velocity, VCM. And because it is rolling, in pure rolling, so the condition is VCM equal to R omega. This condition is valid. Now centrifugal force radially outward is mv square by r. Gravity acts vertically downward, which is mg. So if it has rotated by an angle theta, what is the component of gravity towards the radial line passing through A? So if this angle is theta, then this angle is also theta. This means the component of gravity passing through A is mg cos theta, right? And this is a normal reaction. Now the question is asking to find the theta when this n is equal to 0. So let us form the equation for this. So mg cos theta must be equal to, so for the cylinder to lose contact, the mg cos theta must be equal to mv square by r. So this is your equation 1. Now obviously by this single equation I cannot get the value of theta, so this means I need another equation. And in case of rolling, what equation is valid? It is the conservation of mechanical energy, as the point of contact with the ground, which is the I core or instantaneous center of rotation, does not perform any work because the displacement is 0, because that point, which is point A here, is momentarily at rest. So this means I can apply u plus k equal to constant throughout the rolling object. So if I take the reference frame passing through point A, at this initial moment, what is its kinetic energy? The kinetic energy is 0. Where is the center of mass? The center of mass is here at the center. So this means the radius is r, the center of mass is at a height r. So what is the potential energy? The potential energy is mgr. And when this cylinder has come to this position, let me call this as the final position, where this cylinder is on the verge of losing contact, at this time, at this position, the cylinder will have two forms of kinetic energy. One is translational, another is rotational. So translational kinetic energy will be half mv square, and the rotational kinetic energy will be half, as it is a solid cylinder, so m r square by 2 into omega square, half I omega square. That's the formula. So what I am getting is mv square by 4. So if I add the translational kinetic energy and the rotational kinetic energy, I get the combined kinetic energy of rolling for a solid cylinder, which is equal to, I can write here, it is K equal to 3 by 4 mv square. And what is the potential energy? That means its height, the height of the center of mass from the reference frame. What is the reference frame? The table. So how much high the center of mass is from the table at the time the cylinder has rotated by an angle theta? You can easily see that height is this height, and it is r cos theta, right? So the potential energy at that instant U is equal to mgr cos theta. The summation of kinetic energy plus potential energy initially and the summation of kinetic energy and potential energy at the angle theta must be equal, because energy conservation in case of rolling. So what I can use? I can use 0 plus mgr is equal to mgr cos theta plus 3 by 4 mv square. This is my equation 2, and this is equation 1. So from equation 1, what I can see is that if I cross multiply this radius, I am getting mv square as mgr cos theta. So the equation is coming as mgr cos theta plus 3 by 4. Instead of mv square, what I am getting from here, if I cross multiply the radius, I am getting mgr cos theta. And here also you have an mgr. So cancel the mgr and you get 1 is equal to, the left hand side is coming as 1, and this is equal to coming 7 by 4 cos theta, right? Our target is to calculate theta. So what is cos theta? Cos theta is 4 by 7. So theta is equal to cos inverse 4 by 7. So this is the angle of rotation of the cylinder at the instant the cylinder is on the verge of losing contact. Now we have to also calculate the velocity. So second part of the question is asking that when the cylinder has rotated by this angle theta, so I'll redraw the diagram. The cylinder is now here. It has rotated by an angle theta. We need to calculate the velocity of the center of mass. So this is the reference frame, this is the vertical line, and this is the point A, the radial line passing to the center of mass. And the velocity equation from here, what I am getting, it is coming as mv square by r equal to mg, this angle is theta, into cos theta. But cos theta, we just calculated cos theta as here 4 by 7. So I'll put the value of cos theta equal to 4 by 7. So if I put here, we cancel the mass. So v square is coming as 4gr by 7. Our target is calculation of v. So v is root under 4gr by 7. So this is the velocity of the center of mass when the cylinder has rotated by an angle theta and is on the verge of losing contact. Now second, and there is a third part. Now there is a third part of the question. And the third part of the question is asking that when the cylinder, which was at the edge, the center of mass was vertically up. Now during rolling, after losing contact, the center of mass will come to the horizontal level. When the cylinder comes to this level, what will be the ratio of translational kinetic energy to rotational kinetic energy? We need to find out the ratio of this value. Now see that the moment the cylinder loses contact with the surface and beyond, at every moment, what I can see is that, suppose if this is the edge of the table and the cylinder is anywhere, wherever it is, the gravity always acts through the center of mass, because other than gravity there is no force, right? So after losing contact there is no other force, because normalization also has become 0 and the friction on the edge of the table also has become 0 because it has lost contact. So what is the torque of mg about the center of mass? It is 0. This means that because the torque is 0, the cylinder is not going to increase its angular velocity, because angular velocity can only increase if there is an unbalanced torque. As there is no unbalanced torque, the omega remains constant. This means that whatever angular velocity the cylinder gains during the contact loss, the cylinder will maintain that omega for the rest of its journey. Now, what is that omega? So, V is equal to root under 4gr by 7, and for rolling V is equal to r omega. That means the omega value is 1 by r root under 4gr by 7, and the cylinder will maintain this omega for the rest of its journey because there is no other force acting other than gravity. So, when this cylinder has become horizontal, the center of mass has come to the same horizontal level as that of the table, the omega is exactly same as that when it was losing contact with the edge of the table or with the table. So, what is the rotational kinetic energy at this instant? It will be same omega, right? Because there is no unbalanced torque. So, rotational kinetic energy will be half moment of inertia of cylinder is mr square by 2 into omega square, means this term, this omega square. So, what I am going to get? 1 by r square into 4gr by 7. So, if I cancel this, and 2 into 2 4, it cancels out. So, rotational kinetic energy will be mgr by 7, right? So, denominator I got, it is mgr by 7. Now, what is the translational kinetic energy? Because of gravity, there is some acceleration and the cylinder has gained some velocity. Now, how will you calculate the velocity? Now, if you want to calculate the velocity by using calculus, it will have complex equations. Instead of that, what we can do is that we can bypass that complexity of calculation, and we can do that by energy conservation. Because gravity is a conservative field, and in case of rolling, friction does not do any work. This means that the entire motion, the journey from this initial point till when the center of mass is on the same horizontal level, everywhere there is only conservative force. That means I can apply conservation of energy. So, what was the total energy when the cylinder was initially at rest? It was only mgr, because the center of mass was at a height capital R from the reference frame. Now, when it has come here, center of mass, now see, center of mass is on the same reference frame level, right? Center of mass has come here, it has come to the horizontal level. So, what will be its potential energy? It is going to be 0. What will be the translational kinetic energy? I have no idea, but it will have a rotational kinetic energy, and its value is mgr by 7. So, translational plus rotational, whose value is mgr by 7, this summation must be equal to mgr. So, what is the value of the translational kinetic energy? If you do the side change, you get mgr minus mgr by 7, which is equal to 6 mgr by 7. So, what is the ratio of translational kinetic energy to rotational kinetic energy? The answer is 6 mgr by 7 divided by mgr by 7, and cancel the mgr by 7, you are getting the answer as 6:1 or 6. So, I hope that you like this video, and I'll make more such videos. Thank you for watching. Please do like and subscribe. Tata, see you in the next video.